Thanks for joining this session called Persistent Data Agility and Resiliency at the Edge. My name is Tom Prohofsky, and I am in the office of the CTO at Seagate. If you generate or manage edge applications that are data hungry, you are in the right spot. I'm going to start with the bottom line up front. In this session, I'm not going to talk about adding yet more layers of complexity between your storage and containers, but removing complexity with available open source tools, keenly targeted edge deployments. Our goal is agility. We strive to give the Kubernetes orchestrator as much control as possible to quickly and optimally pair pods with storage at the far reaches of the deployment if necessary. The enemy is complexity, which shows up and slows down both humans and the applications. As we tackle this giant of complexity, we also reduce the need for storage servers and storage network traffic. The end result is more performance with better server optimization. As we look at what the cloud is, we need to define where's the edge. And so to start, we can use terms like macro edge or metro edge or micro edge to help us discuss all the potential locations of the rapidly expanding fringe of deployments. For the sake of this session, let me use the term edge to mean everything that is not the core. Where the core is the use of public clouds or major data centers. Current core options are fantastic at expanding compute, network, and storage, but they typically have a few pain points. Those pain points show up when attempting to address storage requirements that are difficult for the core. First on the list is low latency. When the core is physically located far from the edge, unavoidable flight time latency is added to every I/O. Applications looking for sub-millisecond response times just can't be serviced over the long distance. The second difficult requirement is handling a lot of storage. To move just one drive's worth of data takes hours over a 10 gigabit per second WAN link and over $900 of egress fees at a nickel a gigabyte. The next on the list is geographic control. Governance and regulations or company policies dictate special handling of sensitive data that may need absolute control of data's location. So at the heart of edge computing is where to compose or pair the combination of data and the consuming services. Orchestration can offer optimal pairing on edge compute resources physically close to the source of the data. Once we decide we're moving the container to the data, we can look at how close can we get these two. The shortest path between the container and the physical storage device can be shown as just a few layers through the kernel. In practice, many storage layers come in and inject multiple levels of complexity and bottlenecks. One of those examples is using NFS. If we take a close look, we see two network stacks consuming CPU and DRAM resources. Also, this implies network switching that adds more delay and deployment costs, especially for high bandwidth, low latency solutions. With Kubernetes, local storage solutions offer the shortest path, but we lose some major benefits of cloud-native orchestration. The persistent volume claims stored locally are not fault tolerant on another server. Now deployments need to figure out how to use stranded storage and not overload the CPUs for a given node. Rebalancing storage and CPU pairings requires a complete copy of the data while it's not changing. So we need to add something to address these issues. The storage server is full of possible ways to regain server fault tolerance. I want to briefly look at a few of these solutions at a high-level grouping. The first is the use of distributed file systems. A high-performance enterprise solution has a lot going on in the background, consuming server resources for metadata lookups and resiliency. If the application is designed for multiple pods on multiple servers to share data at the file or block level, then this may be a good call. If the persistent volume is serviced by just one pod instance, then latency and complexity is not required. Hyperconverged infrastructure can aggregate either block or file. Either way, data resiliency comes at the cost of adding network, CPU, and DRAM resources to the mix. Either of these solutions can be deployed with a private storage network or not. Without a dedicated network, application network traffic gets commingled and latency-sensitive storage traffic potentially slowing down both the application and the storage. Any one specific solution comes with varying degrees of added latency and resource consumption, requiring yet more management tools to get control of complexity and quality of service. Let me propose an alternative using the trusted open source project known as LVM2. SAS connects 48 gigabit links for each server without the cost or hassle of managing a low latency, high speed Ethernet switch. This flattens the architecture and connects every server to every drive through the JBOD's expander. You may be asking, how do we prevent servers from overwriting another server's work? The answer comes by leveraging the external locking methods built into LVM2. With the appropriate CSI driver, persistent volumes are provisioned from a pool that is seen symmetrically by all servers. This means the orchestrator can start and migrate pods to any node in the edge cluster. Multiple storage classes manage the quality of service for PVCs out of the same physical pool of SSDs. To understand the role of LVM2 in provisioning persistent volumes, we need to look at how metadata is updated on the drives. Even with just one server, LVM2 must create a locking or barrier operation to prevent numerous internal CPU cores from attempting to simultaneously allocate the same disk blocks. LVM2 creates file locks that are memory structures for all configuration changes to resolve contention. When another server is attached to the same drives, the memories are isolated, preventing this method to being used to cluster servers in cooperation. The LVM2 project created two methods of external locking to support multiple direct attached servers. The first method is the distributed lock manager that uses a network protocol to gain consensus between servers. While possible to get working for normal, healthy cases, the duplicate state on an independent bus creates corner cases that are tough to get bulletproof in design and test, adding complexity and constraints to the deployment. A second method called sandlock uses a region on the drives to create a lock consensus. This is using the same data path to the drive, which helps remove the corner cases from the first approach. The consensus relies on a distributed algorithm and timing windows so servers can walk state machines identically, which bring another set of corner cases. Currently, some of these corner cases require all servers in the cluster to reboot. This is unacceptable for any kind of production deployment. Seagate created a third method that assists in the locking process better than normal reads and writes. The drive now has a quick and definitive answer to the state of locks for all servers symmetrically. This solution is both exhaustively testable and scalable. Only the drives servicing the particular logical volume for the persistent volume claim are involved. This method has been upstreamed to the LVM2 project. So stepping back up, at the end, we're not adding another layer of technology, only using the full capability of Linux's block I/O stack of going in where LVM2 sits in the kernel and expand its role through its external locking mechanism. So LVM2 has the built-in capability of preventing other servers from activating volumes that are being used elsewhere. So that solves the multiple server contention problem of so Kubernetes CSI driver can dynamically provision and assign with this reliable locking mechanism across multiple servers. Plus, we get all the features and maturity of LVM2 as we use this solution. Here's a quick example of how storage class parameters control the creation of persistent volume claim. By specifying RAID 10, we now dictate that all data will be written to 2 drives simultaneously. Specifying stripes equal 8 means each of the leg of the mirror will have 8 physical drives participating. This enables the potential of high throughput and spreads the load. I flipped on no sync for the rapid creation because I know that our drives always respond with 0 when reading unmapped data. So no need to fill the array with zeros when the volume is created. Each persistent volume created with the storage class will have the same performance and resiliency. Another simple striping storage class can be running using the same pool of drives. One great benefit of shedding layers is improving transparency and visibility. By adding a serial number to each Prometheus metric, we get a complete view of the server's raw block traffic down through the persistent volume to the individual drives. In this example, you can see on the top right that we are writing at 8 gigabytes a second of aggregated traffic through 4 servers. That's going through RAID 10 volumes, so you see in the middle on the right 1 gigabyte per second of traffic to each of the persistent volume claims. And then in the bottom you see the 16 drives that are all servicing this workload. So we can go from server through the virtualization of the persistent volume down to the drives with full visibility of using Prometheus and Grafana. I'm going to go back to our first slide now, and as you can see, we have using LVM2 and its external locking mechanisms, we've gotten rid of bottlenecks and we've lowered latency with this direct connect. Complexity is reduced while we now have open source through the whole stack. There's no storage servers that you needed to purchase to manage storage traffic, and no extra storage area network. Power consumption is brought down because of the physical removal of these servers and switches. In the end, we've given the Kubernetes more control over service levels with more visibility and composability. So Kubernetes can come up with that optimal pairing of storage and location of compute. In the end, that means more performance. Here's a few links to leave you with. The first 2 are more information on LVM2 for developers and solution architects. The third link is to documentation about the open source project LinStore that offers edge-to-edge or edge-to-cloud replication. This is clustered LVM2 aware. I also added a link to the Open EBS local PV project that has in its backlog support for clustered logical volumes. So look for that coming soon to be able to use that driver if you so choose for your CSI driver. If you're interested in a demo or learning more, please feel free to contact me by email. Thanks for watching.